Time feels simple. A number on your phone, a clock on the wall, a rhythm we trust without thinking. It's always there, steady, predictable, quietly guiding every moment of our lives. We rarely question it. We rarely wonder how it works. We simply assume time is universal and absolute. But inside a computer, time is anything but simple. It drifts. It disagrees. It fractures into tiny inconsistencies. It must be constantly corrected, negotiated, and aligned. A computer doesn't feel time the way we do. It counts it. It simulates it. It constructs time from electrical pulses and imperfect crystals, a fragile illusion built on physics, math, and trust. And when millions of machines must work together, that illusion becomes even harder to maintain. Every server has its own heartbeat. Every network introduces delays. Every system believes its own version of now. Today, we're going inside the machine to see how computers measure time, how they lose it, and how the entire internet works together to keep the world in sync. From quartz oscillators to atomic clocks, from drifting seconds to global synchronization. This is the hidden story of time in the digital world. Every computer has a heartbeat, a tiny quartz crystal vibrating millions or billions of times per second. It's small enough to fit on your fingertip, yet powerful enough to orchestrate an entire digital universe. Inside that crystal, atoms push and pull in a perfect rhythm, creating a pulse that never stops unless the machine does. When electricity flows through it, the crystal oscillates at a precise frequency. These vibrations become the clock signal, the metronome that coordinates every operation inside the CPU. Tick, tock, on, off. A binary heartbeat that defines the pace of computation. Every instruction, every calculation, every pixel drawn on your screen. All of it happens on the rising and falling edges of this clock. Nothing moves without it. Nothing waits outside its rhythm. This is the computer's sense of time, a world measured not in seconds, but in cycles. Billions of tiny moments, each one a chance for the machine to do something new. But it's not perfect. This heartbeat can drift. It can speed up, slow down, or fall out of sync with the rest of the world. And when millions of computers depend on precise timing, even the smallest drift becomes a problem. Quartz crystals are precise, but not flawless. They vibrate with remarkable consistency, yet they're still bound by the laws of physics. And physics is never perfect. Temperature changes, aging, and microscopic imperfections cause drift. A computer might gain or lose milliseconds every second, barely noticeable to us, but significant inside a machine that lives in nanoseconds. One machine drifting isn't a big deal, but thousands of machines drifting in different directions? That's chaos. Not dramatic, cinematic chaos, but a quiet, invisible kind that breaks systems from the inside. Imagine two servers recording the same event, but one thinks it happened before the other even received it. Suddenly, logs don't line up. Transactions appear out of order. Security checks fail. Distributed databases disagree about what just happened. Reality becomes inconsistent. And in computing, inconsistency is the enemy. It's the moment when truth fractures into multiple versions, each one technically correct from the perspective of its own drifting clock. This is why time matters, not just as a number on a screen, but as the foundation of order, causality, and trust in the digital world. In a distributed system, time becomes a negotiation. Every message takes time to travel. Every network has delays. And no machine can instantly know what time another machine believes it is. Two computers might be separated by a continent, or by a single switch in a data center. But in both cases, the truth is the same. They live in different realities, each defined by its own drifting clock. When one machine sends a time-stamped message, the receiver has no idea how long that message spent in transit. Was it delayed by a busy router? Did it take a slower path across the network? Did it arrive early or late or right on time? There is no universal now in a distributed system. Only local time and the uncertainty between them. This is one of the hardest problems in computer science. How do you make many independent clocks agree on a single timeline? How do you build order out of delay, drift, and incomplete information? Because without a shared sense of time, systems can't agree on what happened first, what happened last, or whether something happened at all. And in a world where billions of machines must cooperate, that uncertainty becomes a fundamental challenge, one that engineers have spent decades trying to solve. To solve this, computers use the Network Time Protocol, NTP. NTP compares your computer's clock with trusted time servers around the world, measuring tiny differences, estimating network delays, and slowly steering your system back toward accuracy. At the top of the hierarchy are atomic clocks, the most accurate timekeepers humans have ever built. They don't rely on quartz or temperature or aging materials. They measure time by the vibrations of atoms themselves, a rhythm so stable it drifts less than a second in millions of years. Below them are Stratum 1 servers directly connected to these atomic sources. Then Stratum 2 servers, which sync from Stratum 1. Then Stratum 3, and so on. A cascading network of machines distributing time across the internet. Like ripples spreading from a single, perfect drop. Your computer sits somewhere in this hierarchy, quietly listening to multiple time servers, comparing their answers, discarding outliers, and calculating the most trustworthy version of now. When your computer drifts, NTP gently nudges it back, never jumping suddenly, never shocking the system. Just slow, careful corrections. A tiny adjustment here, a fractional slowdown there, until your machine falls back into rhythm with the rest of the world. It's a global choreography of clocks, all working together to maintain a shared sense of time across billions of devices. But some systems need more than milliseconds. Financial trading, robotics, 5G networks, power grids. In these worlds, a millisecond isn't small. It's enormous. It's the difference between profit and loss, between stability and failure, between a robot moving safely or dangerously out of sync. For them, NTP isn't enough. They need something sharper, faster, more exact. They use the Precision Time Protocol, PTP, a system built for environments where timing must be nearly perfect. PTP doesn't rely on software guesses or network assumptions. It uses hardware timestamping, capturing the exact moment a packet enters or leaves a network interface, down to the microsecond. Specialized switches pass these timestamps along with minimal delay, creating a chain of precision that stretches across entire factories, data centers, and communication networks. With PTP, machines can synchronize to within microseconds, a level of accuracy that feels almost unreal, compared to the drifting quartz clocks inside ordinary computers. In these environments, time isn't just a convenience. It's a requirement, a foundation, a contract that every device must honor to keep the system safe, stable, and predictable. Because when machines move fast, when decisions happen in microseconds, and when the cost of being wrong is measured in millions, precision isn't optional. It's everything. But what if physical time can't be trusted? What if network delays make it impossible to know the true order of events? What if two machines see the same moment differently, each convinced it's correct? In those cases, computers use something different: logical time. Logical time doesn't care about seconds or milliseconds. It doesn't rely on drifting crystals or imperfect networks. It focuses on something deeper: the relationship between events. Lamport clocks and vector clocks don't measure seconds. They measure causality, the order in which events happen. They track the happen-before relationship, a kind of digital cause and effect that exists even when physical time is unreliable. Instead of asking what time is it, they ask what happened before what, which event triggered which message influenced which decision. It's a different kind of time, a time built not from oscillations or atomic vibrations, but from the structure of communication itself. In a distributed system, reality is fragmented across machines. Each node sees only a slice of the world, a partial timeline shaped by the messages it receives. Logical time stitches those fragments together. It creates order where physical time fails. It gives distributed systems a way to agree on the sequence of events, even when they can't agree on the clock. It's not time as humans experience it, but it's the kind of time computers need to make sense of a world where now is never the same everywhere. Today, synchronized time is the invisible infrastructure of the digital world. It's the quiet foundation beneath everything. Unseen, uncelebrated, but absolutely essential. AI clusters rely on it. Massive neural networks spread across thousands of GPUs must agree on when data was created, shared, and updated. Without shared time, training collapses into confusion. Blockchain networks depend on it. Every block, every transaction, every piece of consensus is anchored to a timeline that all participants must trust. If the clocks drift, the chain fractures. Autonomous vehicles navigate with it. Cars, drones, and robots coordinate their movements. based on timestamps measured in microseconds. A tiny disagreement in time can mean a massive disagreement in space. Satellites orbit using it. GPS doesn't work without synchronized clocks. In fact, your location is calculated by comparing the time signals from multiple satellites. If those clocks drift, the map becomes meaningless. Without accurate time, the modern world simply wouldn't function. Financial markets would desynchronize. Databases would corrupt themselves. Communication networks would fall out of rhythm. And the systems we depend on every day would lose the order that makes them reliable. Time is the hidden architecture of technology, the silent agreement that keeps billions of machines moving together as one. Computers don't experience time the way we do. They don't feel seconds passing. They don't sense mornings or nights. They don't age or wait or remember. They simulate time. They negotiate it. They fight against drift and uncertainty to create the illusion of perfect order. Inside every machine, time is a construction, a delicate balance of oscillations, corrections, and agreements, a rhythm that must be constantly maintained so the digital world can move as one. And that illusion, that fragile, carefully synchronized heartbeat, is what makes everything possible. Our networks, our communication, our navigation, our entire technological reality. Behind every message you send, every video you stream, every transaction you make, there's a quiet choreography of clocks, working tirelessly to stay in sync. It's a reminder that even in a world built on logic and precision, there is still fragility, still uncertainty, still a kind of digital heartbeat that must be protected and preserved. Thanks for watching, and I'll see you in the next chapter of this digital adventure.